In this video, I want to start a discussion of the definition of a ring homomorphism given in Conrad's notes and how it's different from the definition given in Dummit and Foote, and what things result from these differences. So let me just start with what this definition is. This is definition 3.1 in Conrad's notes on standard definitions for rings. Let's say that R and S are rings. A ring homomorphism, phi from R to S, is a map that satisfies phi of x plus y equals phi of x plus phi of y for all x and y in R. Phi of x times y equals phi of x times phi of y for all x and y in R. And one additional thing, phi sends the multiplicative identity of R to the multiplicative identity of S. So this doesn't appear in Dummit and Foote's definition. For one thing, R and S don't even have to have multiplicative identities. So the key thing here is that the multiplicative identity of R gets sent to the multiplicative identity of S. That's the only additional change. So let's talk about why you might require that. And let's go back to this example that we have of this subset 0, 3 inside of Z mod 6Z. So let's take the example of phi from Z mod 6Z to Z mod 6Z defined by phi of x equals 3 times x. It is true that this satisfies the first two properties. Phi of x plus y equals phi of x plus phi of y. 3x plus y is 3x plus 3y by the distributive law, which is phi of x plus phi of y. Less clear is that phi of x times y, that's 3xy, but 3 equals 3 squared. So this is the same as 3 squared xy, which is 3x times 3y, which is phi of x times phi of y. But phi of 1 is not equal to the multiplicative identity of Z mod 6Z. It's equal to 3. So what's the problem in this example is going back to the very beginning of this lecture. Remember, we saw some statement that looked like the first isomorphism theorem for groups. And that's one thing that we're going to want to preserve here is that, what is the image of this map is just 0 and 3. So there's something going on that's different in this example. So this is not a ring homomorphism. So now I'm going to pause and erase, and I'll talk about some things that you can prove with this definition of a ring homomorphism that are nice properties that you would want maps between rings to have. Let's discuss two things that you can prove with Conrad's definition of ring homomorphism. So first, let's say that phi is a ring homomorphism from R to S. Then where does phi send the units of R? It sends them to a subset of the units in S. And more than that, if you take phi and you restrict it to the units in R, you get a group homomorphism from the units of R to the units of S. Let's prove this. If you have a unit in R, x, then x times y, there's a y, so that x times y equals y times x equals 1, the identity in R. And you can just apply phi to all of these equal things. Phi of xy is phi of x times phi of y because phi is a homomorphism, ring homomorphism. And this is phi of 1. And we know that phi of 1 is the multiplicative identity of S because that's part of the definition now of being a ring homomorphism. So this part of the statement is just not true if you don't require that a ring homomorphism sends the identity of R to the identity of S. So this statement is not true in the case where you have this like subset 0, 3 inside of Z mod 6Z example. So if you take the homomorphism that we just talked about in the previous example, that without the extra requirement that it sends the identity to the identity, this statement falls apart. And here is why. Okay, same thing on the other side. Phi of y times x is phi of y, phi of x, which is phi of 1, which again is the identity of S. So what is this saying? X is some unit in R. It gets sent to a unit in S because we have phi of X and phi of Y. Phi of Y satisfies the things necessary to show that phi of X is a unit in S. So phi sends units in R to units in S. So we're seeing that phi sends this group of units to a subset of the group of units in S. But more than that is true, it preserves some structure. So phi is a multiplicative function, meaning that phi of X times Y is phi of X times phi of Y, because phi is a ring homomorphism. So that's exactly the property you need to check to show that phi restricted to the units in R gives a group homomorphism to the units of S. Okay, let's talk about one more consequence. Suppose you have a subring R prime of a ring R. One thing you can do is just take the inclusion map that sends everything in R prime to the corresponding to the same element in R. This is a ring homomorphism. So it's clear, this part, that this inclusion map applied to X plus Y is I of X plus I of Y. I of X plus Y is X plus Y. Now, think of these as elements in R prime. Think of these as elements in R. But, okay, this is clear. And the inclusion map applied to XY is X times Y as elements of R, which is I of X, I of Y. So there's nothing interesting going on here. But if you want this to be a ring homomorphism, you also want to check that it sends the identity of the first ring to the identity of the second ring. And you take I of the identity of R prime. Well, that's whatever this element is as an element of R. But the identity of R prime is the identity of R, because part of the definition of what it means to be a subring is that R prime and R have the same multiplicative identity. So you can think about what happens if you take this other sort of idea of what it means to be a ring homomorphism, where you take like R equals Z mod 6Z and R prime is just the subset 0 and 3. Now the inclusion map no longer sends the identity of R prime to the identity in R, which is kind of like a weird thing. So I'll pause and erase, and then I'll talk about one more result that connects back to one of the first results that we talked about in this lecture, about the image and kernel of a ring homomorphism. Let's talk about one more important result for ring homomorphisms. Let's say that phi is a ring homomorphism from R to S. Just like we saw at the beginning of the lecture with these looser definitions of what it means to be a subring and a ring homomorphism, the image of phi is still a subring of S. But with these other definitions, kernel of phi is now not a subring of R unless S is the zero ring. So this second statement looks really different from what we proved earlier. And I'll prove this statement, and then I'll say something about it, about this difference. Okay, so let's do the proof. So as before, everything that we did at the very beginning of this lecture goes through exactly the same way. Image of phi is still an additive subgroup of S and is closed under multiplication. That works exactly the same way. And now, what else do we need in order for image of phi to be a subring of S? Is we need image of phi to have a multiplicative identity, and for that identity be the same as the identity in S. So since phi is a ring homomorphism, part of the definition now is that it sends the multiplicative identity of R to the multiplicative identity of S. So the image of phi does contain the multiplicative identity of S. So that's it. So image of phi is a subring. Okay. For the second part, a lot of what we said before goes through exactly the same way, that the kernel of phi is an additive subgroup of R that is closed under multiplication. And at that point, with Dummit and Foote's definition of subring, you're done. Kernel of phi is a subring. But here, we want to talk about whether or not kernel of phi is a subring of R. And the big difference is that now all we're asking is the identity of R in the kernel of phi? Because with the definitions that we've been talking about from Conrad's notes, in order to be a subring, you have to contain the same multiplicative identity of R. Okay, so what happens if the answer is yes? Then that means the identity of R is in the kernel of phi, so phi sends the identity of R to 0. But now part of the definition of phi being a ring homomorphism is that phi of the identity of R has to be the identity of S. So if the identity of R is in the kernel of phi, in S, the multiplicative identity and the additive identity are the same, 1 equals 0. And that means that S is the 0 ring. So, okay, so what is the difference going on here versus the property 5 from the beginning of lecture that we proved from Dummit and Foote? Is the big difference is about the multiplicative identity, right? So here, to be a subring, we're requiring that you contain the multiplicative identity of R. Whereas in Dummit and Foote, that's not part of the requirement. So I'll pause and erase and get a little bit of space and just give some remarks from Conrad's notes about this difference. After stating and proving this theorem 3.5, Conrad writes, this last theorem is probably why some people do not insist that rings contain a 1. What is it that these people want is some kind of parallelism between homomorphisms for groups and homomorphisms for rings. So what do I mean? The kernel of a group homomorphism is a subgroup. And in fact, it's a special kind of subgroup. It's a normal subgroup. And more is true, every normal subgroup comes from this procedure. Every normal subgroup is the kernel of a group homomorphism. So maybe it's a little bit disturbing at first to say that the kernel of a ring homomorphism now is not a subring. Kernel of a group homomorphism is a subgroup. The kernel of a ring homomorphism is not a subring because it generally does not include the identity. It doesn't have a 1, so it doesn't get to be called a subring. But a lot of this actually does go through. It's not a subring, but it is a special kind of thing. And what is that thing? That is an ideal. And what we're going to see is an analog of the third part is true as well, where like every normal subgroup is the kernel of a group homomorphism. We'll see that every one of these special objects, these special subsets that are ideals, these are all going to be kernels of ring homomorphisms. So in the next video, I'll take this vague hinting and turn this into a real definition and tell you what an ideal is and say a little about the relationship between ideals and subrings.